To operate inside the human eye, a surgeon must routinely navigate structures at the limits of human visibility. The neural retina is roughly 150 microns thick. A target blood vessel might be 80 microns wide, and the internal limiting membrane, a delicate layer that sometimes needs to be peeled away to resolve vision issues, is a mere 5 to 10 microns across. At this microscopic scale, a single unintended kinetic deviation can easily tear a membrane or puncture a choroidal vessel. The primary barrier to achieving this level of accuracy is the human musculoskeletal system itself. Even under rested conditions, a highly trained surgeon's hand naturally produces a physiological tremor, an involuntary, rhythmic oscillation superimposed directly on their deliberate movements. This chart illustrates the spectral density of that human movement. Notice the red peak here. Biomechanical studies consistently show that the dominant frequency of physiological hand tremor resides squarely in the 8 to 12 Hz band. Looking at the lower section of this chart, we can see the physical displacement this tremor causes in real space. A rested surgeon's hand deviates anywhere from 50 to 200 microns. This means an operator attempting to cannulate an 80-micron retinal vein is actively fighting a biological oscillation that is frequently larger than the target vessel itself. Because we cannot biologically stop the human nervous system from firing, achieving true microscopic precision requires physically decoupling the surgeon from the scalpel. The Da Vinci surgical system solves this utilizing a master-slave teleoperation architecture. Instead of holding the instrument directly, the surgeon sits at a remote console, manipulating high-resolution controllers, while a patient-side cart with robotic arms replicates those movements inside the body. This diagram maps out the digital signal processing pipeline that makes this physical separation possible. To maintain the illusion of direct manipulation, central processors sample the surgeon's exact hand position once every millisecond, a 1000 Hz sampling rate. Within that 1 millisecond window, raw positional data runs through a digital low-pass filter. It allows low-frequency signals to pass through while reducing the amplitude of high-frequency noise. By setting the cutoff at 2 Hz, the system lets the surgeon's deliberate movements pass to the robotic arms, while the biological tremor is effectively deleted. This chart demonstrates the final stage of the filtration process, known as motion scaling. The system mathematically shrinks a large hand movement down to a tiny robotic movement. If a 3-to-1 ratio is selected, the surgeon moves their hand 3 centimeters in the air, but the robotic tip only moves 1 centimeter inside the patient, drastically improving the signal-to-noise ratio. As this bar chart shows, the resulting stability is striking. While an unassisted human hand generates up to 182 microns of spatial deviation, the robotic intermediary strips the biological noise away, reducing the residual motion at the instrument tip to just 20 microns, a fraction of the width of a human hair. The robot doesn't physically study the surgeon's hand. Instead, it acts as a computational intermediary that mathematically purifies intent before translating it into physical action. But separating the operator from the instrument introduces a severe sensory deficit. By dropping a computer between the hand and the tissue, the surgeon loses all physical sense of tactile resistance and tension. For over 2 decades, robotic operators compensated using a technique called visual haptics. Relying on stereoscopic 3D vision, surgeons watched for secondary visual cues, like tissue blanching, where the mechanical pressure of a grasper forces blood out of capillaries, to mentally estimate the physical force they were applying. The latest Da Vinci 5 platform addresses this blind spot directly. Engineers embedded highly sensitive strain gauges directly into the distal tips of the instruments. These sensors measure exact physical resistance at the tissue level and mechanically transmit those push and pull forces back to the surgeon's hand controllers in real time. Delivering this kind of precision and feedback inside a patient requires navigating a massive physical constraint. The heavy, heat-generating direct current motors required to produce surgical torque are too large to fit through tiny incisions, so they are housed externally on the robotic arm, outside the sterile field. To transfer power from external motors down an 8mm rigid shaft, the system relies on a complex network of microscopic pulleys and braided tungsten cables. Tungsten boasts nearly 30% more tensile strength than medical-grade stainless steel. More importantly, when braided, it behaves less like a stiff wire and more like a strand of cooked spaghetti. This lack of shape memory allows the cables to navigate sharp internal radii, recreating the 7 degrees of freedom of a human wrist deep inside the body cavity. Yet this reliance on microscopic cables introduces a harsh physical reality. Operating complex internal linkages under high tension causes immense mechanical friction and rapid flexural fatigue. This life cycle diagram illustrates the resulting stress vectors. During active surgery, these ultrafine cables rapidly navigate static guide channels and tight angles, causing tension to spike by up to 67%. This intense intraoperative load forces the tungsten to undergo progressive metallurgical stretching, a permanent elongation that disrupts the exact kinematic mapping of the instrument. Furthermore, the intricate crevices of the whisk mechanism are exceptionally difficult to clean. Exposing these delicate joints to the aggressive thermal expansion and 132-degree pressure waves of a hospital autoclave accelerates the degradation of the materials. If these microscopic cables continue to stretch, the mechanical tolerance drifts, creating measurable play or hysteresis in the instrument tip. Over successive cycles, the loss of resting tension exponentializes the risk of a catastrophic cable snap midway through a delicate procedure. Infinite mechanical durability is physically impossible at this microscopic scale. To prevent mid-surgery failures and ensure patient safety, the manufacturer had to intervene and strictly regulate the life cycle of its hardware. Intuitive Surgical solved this engineering constraint by capping the vast majority of their core instruments at a strict maximum of 10 uses. Rather than relying on hospital staff to track wear and tear, this limit is technologically enforced. Every instrument contains an embedded memory chip that communicates with the central processor. Once an instrument reaches its 10th procedure, the software digitally locks the tool, rendering it permanently inert and forcing the hospital to discard it. What began as a legitimate biomedical safety measure birthed a lucrative financial architecture. By mandating obsolescence through a digital lock, the company established a razor and blades business model, where the continuous sale of semi-disposable instruments generates roughly 3/4 of its multi-billion-dollar annual revenue. Hospitals that spend millions on the initial capital equipment are structurally locked into an endless reorder cycle. With global procedure volumes growing by double digits every year, the required consumption of these instruments scales perfectly in tandem. Intuitive Surgical's multi-billion-dollar monopoly grew from the intersection of human biology and the laws of physics. The company solved the mechanical failures of the microscopic world, and in doing so, engineered a predictable, inescapable revenue engine.